The last third of this section is calculating the volume of solids that have a known cross-section. So we have been finding the volume of a solid that has a circular cross-section. We can do that pretty easily, actually. We can find the volume of any solid as long as it has a known cross-section using what you're about to learn here. All we have to have is a formula for the area of the object's cross-section. If we have that, then we can integrate over that entire length of the thing perpendicular to the cross-section. Common cross-sections aside from circles. So we've been working with circles. Aside from those, squares, rectangles, triangles, semicircles, and trapezoids. There's going to be something on the AP exam that involves this. It's almost always there. I should just say it's always there, because it is always there. If a solid is presented to you in a three-dimensional space, so it's just 3D, and the cross-section of the solid is known, meaning they tell you that the cross-section of the solid is whatever, a triangle or something like that, then that means the cross-section is known. So you could cut that object anywhere along that cross-section and see that shape. So you'd see a triangle, or you'd see a rhombus, or you'd see whatever. For cross-sections that have an area as some sort of area defined in terms of x, so it's like a function for the area as you were to move the slider from left to right, and that cross-section is perpendicular to the x-axis, then the volume of the solid is just the integral from where I can start my slider to where I can stop my slider of that area dx. If the cross-section of is taken perpendicular to the y-axis, then your area is going to be defined, or need to be defined, in terms of y, and then your volume is going to be the integral from where I can start that slider at the bottom to where I can slide that thing to the top of the area of y dy. It's very straightforward, but the setup is the tricky part. So once you have it set up and you have an expression for the area in terms of either x or y, depending on which way they're going, then you can integrate very easily. So this is an example of finding the area of a known cross-section, or the volume of a known cross-section. Find the volume of the solid that's shown. The base of the solid is the region bounded by these lines, and also x equals 0. The cross-sections perpendicular to the x-axis are equilateral triangles. So first of all, the language that's given to you is the cross-sections perpendicular to the x-axis are equilateral triangles. So all of this information right here is incredibly important to solving this problem. Cross-sections, now I know that I got to use this process that we're working with. Perpendicular to the x-axis, now I know that I need to define my area of the cross-section in terms of x. Equilateral triangles, that's my clue as to how I'm going to find the area of the cross-section. So this tells me I need the area in terms of x, which is nice because they're already giving me two functions that are defining that area in terms of x. So I'm kind of in good shape already. So the first place we want to start is with this information that they give me. Cross-section perpendicular to the x-axis is an equilateral triangle. So that means I need to define my area as an equilateral triangle. That's going to be my area function. Now take a look at the figure that they're giving me. They're showing me this shape, and it's kind of tough if you haven't worked with three-dimensional figures on a piece of paper before to see that dimension to it. But this is the x-axis right here. This is the y-axis, and then the shape is coming out of that plane, and then this would be like the z-axis if they had drawn it in there. We don't need a z-axis here. We just need to know that the shape is coming out of that xy plane. Okay? Now, it says the cross-section's perpendicular to the x-axis. So here's my x-axis. Perpendicular to that would be like the yz plane coming out of the xy plane, and then also including the y-axis. So that plane right there, that forms my perpendicular to the x-axis. So that means that if I were to cut along that YZ plane, I would see this cross-section right here. That is an equilateral triangle. If I were to cut up here, I would see that cross section right there, and that is an equilateral triangle. If I were to just look at the back side of this shape, that is an equilateral triangle. As long as I'm cutting perpendicular to the x-axis, I'm going to form an equilateral triangle as my cross section. So now what I have to do is define this area of this equilateral triangle in terms of x, because what's going to happen is this little equilateral triangle right here is going to be my slider. It's going to slide from all the way out here all the way back to be this back edge, and then I can slide it all the way forward to be just that point right there. It is still rectangles, but the object itself, the cross section that I'm forming, the cross section that I was forming with the disk method was a disk. The cross section I was forming with the washer method was a washer. The cross section that I'm forming with solids of known cross sections is that known cross section. We're still going to use representative rectangles. We're doing the same thing just with different shapes. Yeah. But we're not revolving around an axis of revolution this time. We're just finding the actual cross section and then sliding it. Okay. So the cross section is given here, and this is the hardest part about these problems, is visualizing this and then going to defining that cross section. So what we're looking at here is the xy plane, which means we're looking at this base of the shape. Okay, do you see that? All right. Now the base of the shape, in my shape, when I make that cross-section cut, I get this equilateral triangle, but the base of that equilateral triangle is this representative rectangle right here. Okay, so this representative rectangle is what I'm sliding back and forth. In the three-dimensional figure, it turns into an equilateral triangle that I'm sliding back and forth. But we're going to look at just this rectangle. So now what we need to do is define this side, the side of an equilateral triangle. Because if I know that side, because it's an equilateral triangle, I'll know that side and I'll know that side as well. What's the area formula for an equilateral triangle? That is the area formula for a triangle. Same thing for an equilateral triangle. So either I can form the area of my equilateral triangle using 1/2 base times height, or I can know the formula for an equilateral triangle's area. Take a look at the back cover of your book. So the formula is area equals the square root of 3/4 times a side squared.
You know, I was thinking that, but then...
So the way that you can find that is by remembering that the area formula for a triangle is 1/2 the base times the height, right? So we have an equilateral triangle sitting here. No, we have a triangle sitting here. This is an equilateral triangle. If I imagine an equilateral triangle, that's a terrible equilateral triangle, but we're pretending that it is one. The height is that length right there, right? Well, the height splits this length right here in half. So whatever that side is, it's been split in half. 1/2 the side, 1/2 the side, right? So now if I find the area of this triangle, if I call that the height, I can find the area of this triangle and then double it. If you work all that out, you wind up with this equation sitting right here. The square root of 3/4 times a side squared gives you the area. So what we need to do is figure out the length of a side. Now remember that we're finding the length of a side of our equilateral triangle. This is not our equilateral triangle here. This is the base. All right? This is my equilateral triangle. I need to find this length right here. So how can I find that length? Yeah, it's f of x minus g of x. So this length right here is going to be my side that I'll put right there. So that means that this length is f of x minus g of x. So now we need to actually form the height of that representative rectangle, because that's going to give me the side of my triangle, and then I can substitute that in right there. So I need to actually find f of x minus g of x. So I'm going to label that the base, because that will be the base of my equilateral triangle right there. So to find the base, and this is just for my own record keeping here, you need to do f of x, which is 1 minus x over 2, minus g of x, which is negative 1 plus x over 2. And then we combine all our like terms. We have 1 minus negative 1, which is 2. And then we have negative x over 2 minus x over 2, which is negative 2x over 2, which is just minus x. So the side length of my representative rectangle, which forms my equilateral triangle, is 2 minus x. So that means that I can find the area then, in terms of x, of my representative cross-section. The area is the square root of 3 over 4 times the side, which we just found, was 2 minus x squared. We're almost there. All we got to do now is figure out where our slider goes from and to. Where can our slider start? 0. And it goes over to?
Possibly 2, but we can't assume.
You can't assume, that's right. So we do have to set them equal to each other. And we have 1 minus x over 2 equals negative 1 plus x over 2. So we add 1 to both sides, we get 2. We add x over 2 to both sides, we get x. So we are going from 0 to 2. Which means now we're ready to set up our integral. The volume formula, one more time, is v equals the integral from a to b of the area of the cross-section in terms of x, because our cross-section is perpendicular to the x-axis, dx. It could be on the AP exam that this is all you have to write. So it's important to know that notation. Now we can substitute our stuff in. We're going from 0 to 2. Our area formula, or our area of our cross-section, is the square root of 3 over 4, but that's a constant, so I can squeeze that in outside. My side is 2 minus x squared dx. Let's not FOIL it out. We can use the practice. So how do I integrate that thing? Okay. So this is the square root of 3 over 4 times. Let's do a U substitution on this. Because last time we tried to do this, it was terrible. Let U equal what? 2 minus x. So then du equals negative 1 dx, which means dx equals negative du. So then this becomes u squared with a negative du. So we have the integral of u squared du with a negative out front. So this becomes negative u to the third over 3. Now we can go back and we have negative, so I'll put the negative sign out front, u, 2 minus x to the third over 3. We're going from 0 to 2. So now we can actually evaluate that. We have the negative square root of 3 over 4. All right, we could pull that 3 out, but that's okay. Times 2 minus 2 is 0, cubed is 0, divided by 3 is 0. So there's actually a 0 sitting here. And then minus. That's a 0, yeah. Sorry. 8/3. So we wind up positive, and we should wind up positive because we're finding a volume here. But it's the square root of 3 times 8, but positive because we're, multiplying negative times a negative and whatnot. So this is 8 square root 3 over 12. Two root 3 over, we're dividing top and bottom by 4, so it's 3. 2 root 3 over 3 is the answer for the volume of that solid with a known cross-section. Yeah, units cubed, whatever they were. Do we have units on this? No. So the difficult thing about these problems is the setup. Right here, this stuff is the hard part. After that, the volume formula for a known cross-section is very, very easy. But finding that A of x or that A of y, that's the challenge. After that, you're good to go. So we have one more practice problem here. Prove that the volume of a pyramid with a square base is V equals 1/3 the height times the area of the base, where h is the height of the pyramid and b is the area of the base. So let's try to talk our way through this. What is the most important thing that we need to see here? This is first of all, it's a pyramid, but it has a square base. Because it has a square base, notice that in this picture, that square base is going to be my slider. It's a square the whole way up. So that means that my cross-section is perpendicular to what? Perpendicular to y-axis. So that means we need A in terms of y. Now it's a square base, so we can use that information to help us define the area of that square base in terms of y. So the important thing is visualizing the fact that as you cut that cross-section anywhere, you're going to have a square when you look at that cut that you made. Now the trick on this one is, how do you define? See, I have this like blow up picture here. What I've done is I've taken that. That's what this is right here. So we're looking at not even like half of the pyramid here. I'm just looking at this side only, head on into that pyramid. Now this cross section here, this representative square that we have, is shown here as a representative rectangle. The reason that we're only taking that one side of that pyramid is because this side is exactly the same as this side, and we can just double it. Okay? Now the base, they're showing you, has a length of b. So if I take a cross-section up somewhere else, then that base is going to have a new length, and they're calling that b prime. That is not the derivative. That's just a different base length. So the notation kind of gets jumbled together as we do more stuff in math. Okay, so what we need to do here is see that we have similar triangles. They have a shared angle, and these are both right angles sitting right here. So these are similar triangles. As soon as we have similar triangles, then we can set up proportions to help us define things in terms of something that we want to define for. Because our problem right now is we have this b prime. sitting here, some other length of the base depending on where this slider is situated. And we need to be defining things just in terms of b, not b prime. So what I need to do is set up a proportion on this. To do that, we're comparing corresponding sides. I need to compare this b prime thing. What can I do? One half b prime, which is this length, compared to this length, which is 1/2 b. So the 1/2s will divide out, equals. So this entire height, this entire length right here is the height of that pyramid. If we define the position of this slider, which is what we're going to be doing in the next section also, by the way, maybe you've done it already on your homework. We're defining the position of the slider in terms of how far away it is from the origin. So that distance right there is y. And if that distance is y and this distance is h, then this remaining distance here is h minus y. So that means that my little base length divided by my big base length is going to be equal to my little height divided by my entire height, which is what? H. Okay, before I solve for b prime, because that is the thing that I need to know, those 1/2s are gone. And now I can solve for b prime. It is b times h minus y over h. So the reason I needed b prime is because I have a square sitting here. I need to know that length. As soon as I know that length, what can I do to it to find the area that I'm looking at? The area of a square is the base, the side length times itself, because it's a square. So it's the side length squared, okay? So this length right here, the b prime, is what I had to find. I find it by taking this, knowing this length is b, so that gives me a 1/2 b. So that means that whatever I'm dealing with up here is 1/2 b prime from geometry. And then I define this stuff so that I can set up my proportion so that I can solve for b prime. And now I know how long this side is based on the length of this side right here. All right, so now that I have the length of this side right here for my representative cross-section defined in terms of the length of the base of the pyramid itself and the height of the pyramid itself, I can go ahead and move on. How do I find the area of my cross-section? It is b prime squared. So that's going to be b times h minus y over h squared, which we can simplify so that a of y equals, it's over, that's an h. All the way back here, it's h minus y over h, because it's the little height minus or divided by the entire height. So it's, okay. So we have b squared over h squared times h minus y squared. Is this a function defined in terms of y? Yes, it is. A of y, and we have a y sitting here. We don't have an x. What is this? What is that? It's a constant. What is this? It's a constant. So here's my variable right here. Okay? So we're basically set to go. We just got to figure out our slider. It goes from what to what? Zero to, we don't know. Well, what is that it's sliding up to? What is it that it's sliding up to? H. H is just a number. I don't know how high that thing goes, but I know that it's H. All right, so we're ready to go. What is my volume equation going to be? Integral from normally A to B of the area in terms of y dy equals. Okay. All right. This is what? So I can write it out front. Let me get rid of this, make more room. So we have the b squared over h squared integral from 0 to h of dy. That's the setup. Again, it could be on the AP exam. They only ask you to get this far. Set it up, but do not solve. But we're going to continue because we're trying to prove this. So, v equals. Now we got to integrate. Okay, so we still have that. B squared over h squared times, in parentheses, h minus y, now to the third power over 3. But we need a negative here because of the undoing of the chain rule. If we were to take the derivative of this, the 3 would come down, and the 3 and the 3 would divide out. This would stay the same to the second power, but then we'd have to take the derivative of what's inside, which would give us a negative 1 out here. So we have to have a negative out front, which means we need a negative all the way out front. And we're evaluating this from 0 to h. We're almost there. So we get v equals the negative b squared over h squared times h minus h is 0 to the third is 0 divided by 3 is 0. So that's just 0 minus h cubed over 3. So we simplify that. The 0 minus that just leaves me with the negative h cubed over 3. The negative times the negative becomes positive, and I get b squared h to the third over h squared times 3, which is 3h squared. That simplifies and gives me the 1/3 out front. The h's simplify, and I wind up with b squared h. But what is b squared? B squared is capital B, the area of the base. So therefore, this is 1/3 capital B h, which completes our proof. We actually have what we were looking for right there.